Hi, I am Sanjay Patel. Today we are going to start the topic of multiple integrals. In this series of lectures, we are going to understand how to compute multiple integrals. Before that, let us recall some basic things from your earlier course. First thing is the fundamental theorem of integral calculus. If you have the function f defined on closed interval ab to r, okay, is integrable function, or you can say Riemann integrable, is Riemann integrable function. Okay, and or you can say simply integrable function, and if there exists a function capital F, okay, which is differentiable on closed interval AB, and if f dash x, the derivative of this capital F, is equal to small fx for every x in this closed interval, then we know that integral a to b fx dx is given by this notation. So we write square bracket capital Fx, where capital Fx is called the integral of small fx, and the meaning of this notation is f of b minus f of a. So what we will do is first substitute x equal to b in this integral, and then minus f of a. You know this very well from your schools. For example, let us take this simple illustration, 0 to 1 x square dx. Okay, all of you know what is the integral of x square. So that integral we write in this square bracket. This is small fx and this is capital Fx. Integral of x square is x cube upon 3, and the limits of integration are 0 and 1. So first we substitute x equal to 1, and we'll get 1 upon 3 minus then x equal to 0. So answer is 1 by 3. Okay, so you know this very well, and I recommend that before you study how to evaluate multiple integrals, you must learn the basic integral formulas for functions of one variable. So whatever integrals you have studied so far, they were all integrals of functions of one variable. So this integrand is only containing one variable. Okay, let me take one more example, just a simple one to recall. The integral 0 to pi by 2, say cos x dx. What is the integral of cos x? Integral of cos x is sin x. Remember, it is not minus sin x. Minus sin x is the derivative of cos x. So integral of cos x is sin x, because derivative of sin x is cos x, and then 0 to pi by 2. And putting the values, x equal to pi by 2, we get sin pi by 2, okay, minus sin 0, and sin pi by 2 is 1 and sin 0 is 0. So final answer is 1. So these are some very basic things, and now we'll see how we can extend this integration of functions of one variable to functions of several variables. So in this regard, we first start with double integral concept, and then we'll introduce say triple integral also, and then you can extend it for multiple integrals in general. So the concept of double integral. Concept of double integral. Double integral is actually integral of a function of two variables. All of you know what is function of two variables. The domain must contain some subset of, say, the plane, the R2, Cartesian plane R2. So let me consider this way. Let f be a function defined from AB cross CD to R. This be a real valid function. This be a real valid function of two variables x and y. Okay. This domain, which is AB cross CD, we can also write it as, just I'm writing as an extra thing here. This domain is a rectangle because AB and CD are the closed intervals, and this rectangle we are going to denote by this notation, this as rectangle A comma B, then semicolon C comma D, so that it is same as AB cross CD. Okay. And to be more precise, our function is something like this. So let me take say this is x-axis, and say okay, just a minute. This is y-axis, okay. And let me name it. This is x-axis, y-axis, origin, and we take the closed interval AB somewhere here on the x-axis, and closed interval CD like this. Remember, AB and CD need not be of same length. So we can have a rectangle as a Cartesian product of this two closed intervals. So I can take this way. This is it is the line y is equal to D. This is the line y is equal to C. Same way, we can take a line it's not proper. Okay, and the same way here. So this is x equal to x equal to A and x equal to B. So our region or the domain of the function is all points in R2 here, which are lying between these lines. So this is our domain and it is our rectangle. Our function is defined from this rectangle R, okay, rectangle R to the set of real numbers. So the codomain is the set of real numbers. Okay. So whatever point you choose in this, so if I take any point here, x comma y, and the function value I will get here as f of x comma y, which is some real number. Okay. So this is called function of two variables, and one simple example to understand what kind of formula is that, you know very well. I can take close interval 0 1 cross close interval say 2 comma 3 to R and define a function like this: f of x comma y is equal to 2x plus 3y. So for any point between this in rectangle, say for x equal to 1 by 2 and y is equal to say 5 by 2, we can have, which is in this domain, we can find the value of the function as 2 into 1 by 2 plus 3 into 5 by 2. Okay, so that is 1 plus 15 by 2. So it is finally 17 by 2. So this way you can understand how one can compute the value of function of two variables. What we are interested in is how to define the integral of such function of two variables. For function of one variable, you know, it is very simple, as I have explained here. This is integral of function of one variable, and now we are going to discuss how to compute integral of function of two variables. The actual understanding and the concept of double integral is very much detailed, and it is out of our scope of this lecture series. It requires a complete independent treatment. Like we start with the Riemann integrals, and as you don't know what is the Riemann integral, we cannot go further, because the concept of double integral is also defined using the upper sum and lower sum, as we have discussed in Riemann integral. So I am just explaining what is the simple basic meaning of double integral and how to compute double integral. Okay, so let us understand. For such a function of two variables, what we have taken here, f from closed interval ab cross cd to r, I want to define the meaning of integral. So this is our definition. Yes. So we define the integral of the function f of x comma y, okay, on the rectangle R. Okay, this is the rectangle R, that is AB CD, as follows. So our definition will be this: double integral of the function f x comma y, okay, dx dy, because there are two variables, over the rectangle R, is defined as integral a to b, okay, and that is x is equal to a to x is equal to b, and y is equal to c to y is equal to d, f of x comma y dy dx. So this will be our formula, you can say, just for simplicity, because you don't know what is the meaning of Riemann integral in details, and that is not point of discussion here. So this can be simply written as integral a to b. We are going to write in this form only, integral a to b and integral c to d f of x comma y dx comma dy. So remember, it is to be integrated with respect to y first, and then with respect to x. So we are going always in this direction, first with respect to this variable and then with respect to this. And the same way, the first outermost integral sign indicates limits of the variable x, and the second integral sign where c and d indicates the limits of variable y. So this is one way of computing the double integral over a rectangle. Okay. Another way is we can write the double integral of f dx dy over the rectangle R is defined as y is equal to c to d and x is equal to a to b f of x comma y dx comma dy. Okay, and that is same as we can write an equivalent symbol for this, which we are going to use throughout our topic of multiple integrals. C to d integral a to b f of x comma y dy dx. Now what is the meaning? How to compute this in practice? Let me explain here. The meaning of this integral, when we want to integrate this first type of double integral, okay, where first we are integrating with respect to y. So whenever we are integrating with respect to y, we keep x constant. So this variable is treated as constant and we integrate. It's something like partial derivative you have studied in differential calculus. So keep x constant and integrate this function as a function of y only, and then substitute the limits of integration y equal to c and d. So what you will get is some expression in x, and now you integrate that expression, which is a function of x, with respect to x, and finally substitute values of the limits of x. Same way, in this is to be integrated with respect to x first, so we keep y constant and we integrate with respect to x. So answer or the result of integration will be something in terms of y. So we get some function of y because we are putting the values of x, a and b after integrating, and whatever function of y we get, that is to be integrated with respect to y, and then finally we put the limits of integration. Let me explain this by actually evaluating some double integrals. So let us take some examples. Let us take some examples. So first example, evaluate the double integral 01 x square y dx dy. Okay, so for this, first of all, write down that given problem x square y dx dy. Okay, so whenever this way it is written, you always understand that it is to be integrated with respect to y first and then with respect to x. So we have to go in this order, and this is first and then this is second variable. So here these are the limits of x and this is the limits of y. So it is actually integral x is equal to 0 to 1 into bracket integral y is equal to 0 to 1 x square y dy dx. Please note that here this is our function f of x comma y, and when we are integrating with respect to y, we keep this x constant. Okay, so this x is constant. So what is the integral of y? Something like, suppose x square value is 4, so 4y. So what is the integral of 4y? It is 4 into y square by 2. So we write like this. This is equal to integral x is equal to 0 to 1. Then here the integral of x square into y. X square is constant, you can write outside also, or you can keep it inside also. Let me write with the integral only. So x square is a constant as it is, and integral of y is y square by 2, and the limits of integration y equal to 0 to 1, and this into dx. Next, this we can write as x equal to 0 to 1, and we simplify this by putting first y equal to 1. Remember, these are the limits of y only, so you have to put these values in place of y wherever it appears in this answer. So x square into 1 by 2 minus, by that fundamental theorem, x square into 0. So what we'll get is integral 0 to 1. This is 0, so simply x square by 2 dx. And you know very well what is the integral of x square by 2. 2 is constant, so it is x cube upon 2 into 3 and 0 to 1. You can keep 1 by 2 outside also. So final answer would be, so it is x cube by 6, so it is 1 upon 6 minus 0. So final answer is 1 upon 6. So value of our double integral is 1 by 6. Let us find the other integral in the same example for the same function but in the reverse order, and let us see what happens. So let me call this as, say, 1 first part, and the second part I'm going to evaluate the same integral 0 to 1 x square y dx dy. Now using that other formula, that is integral, say y is equal to 0 to 1, okay, and x is equal to 0 to 1 x square into y dx dy. So we are integrating first with respect to y. Remember, this is a general notation. I should write, in order to avoid the confusion, let me write y next. So what I'm doing is I am finding the other double integral. Okay, so the meaning here is, first this is to be integrated with respect to x by keeping y constant, and you know what is the integral of x square, that is x cubed by 3. So y is equal to 0 to 1 as it is, and then integral of y is equal to 0 to 1, and integral of x square into y with respect to x. So y is constant and integral of x is x cubed upon 3, and this is x equal to 0 to 1 into dy. One can write like this also. Okay, or let me put one more bracket to make it more clear. And then this I can rewrite as integral y is equal to 0 to 1. Putting the values here, first we put x equal to 1. So y into 1 by 3 minus x equal to 0. So y into 0 dy. So that gives us integral 0 to 1 y by 3 only. And this is again a simple integral. 1 upon 3 is a constant. I can keep it outside of the integral sign. And the integral of y is y square by 2. And these are the limits of y. Y is equal to 0 to 1. So it is 1 by 3 into 1 by 2 minus 0. So again, the answer is 1 by 6. So what we have observed in this example, that the double integral over the given rectangle, that is very important. Let me rewrite. So thus, the double integral of the given function which was x square y over the rectangle R, is, that is, let me write dx dy, is equal to 1 by 6, whether you integrate with respect to x first or with respect to y first. But that is not always the case. Here the function x square into y is a nice function, continuous function. So we are getting both the values, whether you integrate with respect to x first or with respect to y first, both the value of integration are same. Okay, so what we should do is, let us take some other example. Say evaluate the integral 0 to 1, or let me write in a different way. Evaluate the double integral of the function x square minus y square, okay, over the rectangle R. So you can write dr also, where dr means dx dy, because R is a rectangle, where R stands for 0 1 cross 0 1, this rectangle. I can use dr here, or I can write dx dy as a differential of this. Now we are going to integrate this double integral over the region R of x square minus y square, this as integral x is equal to 0 to 1, and integral y is equal to 0 to 1 x square minus y square dx into dy. Remember, here we have both the says intervals are 0 1 cross 0 1. So x belongs to closed interval 0 1 and y also belongs to closed interval 0 1. So we have this x ranges from 0 to 1, that is 0 less than or equal to x less than or equal to 1, and y also ranges from 0 to 1. To integrate this, it is very simple function. What I will get is integral x is equal to 0 to 1, then integral y is equal to 0 to 1 first. So I am integrating with respect to y first. So whenever you are integrating with respect to y first, keep x constant. So this x is constant. Okay, so 0 to 1, when you know the limits, no need to write the variable name x or y. The integral of x square is a constant, with respect to y is x square into y, because integral of 1, integral of 1 dx is x. Similar, integral of 1 dy is y. So x square into 1, because x square is constant, so integral of 1 is y, minus integral of y square with respect to y is y cube upon 3. And this is to be evaluated from 0 to 1. Okay, and the remaining thing as it is. So let us simplify. So we have x is equal to 0 to 1, and when you put the limits of integration, what you will get is putting y equal to 1 first. So we'll get x square into 1 minus 1 by 3 minus, because it is fb minus fa formula. Now putting y equal to 0, so 0 minus 0, because x square into 0 is 0 and this is 0 upon 3. So this is equal to integral 0 to 1 x square minus 1 by 3 dx, which is again a simple integral. So you will get x cube by 3 minus 1 by 3 times x, and the limits of integration is 0 to 1. So it is very easy to compute this value. So final answer, by putting x equal to 1 first, 1 by 3 minus 1 by 3, okay, minus 0 minus 0. So putting x equal to 1 in both the terms, and then putting x equal to 0 in both of this. So final answer is 0, because this is also cancelled. So this way you can compute the double integral over a rectangle. But remember, a function of two variables need not be defined only over a rectangle. So domain of a function of two variables can be any irregular subset of the Cartesian plane R2. Okay, so we'll see in the next lecture how to compute the integral of function defined over any region, and we'll introduce another type of double integral, which is known as repeated integral or iterated integral. So thank you.